Okay, I hope you can hear me. We're going to continue where we left off last time. First of all, apologies that I couldn't make it in person last time. I know some of you like to see it live, like to see it on the internet anyway, so then it doesn't make a difference. But for all of you who like to come here, I'm happy that you are coming in person, and I want to try to be there as much as I can personally and not send videos. Because I think especially after the COVID and the lockdown times, people are a little bit tired of seeing the world through with videos only, and they want to see things for real, and so I'm going to try to make that happen. We talked about activations last time, and today we're going to talk about weight initialization. So the idea here is that you have a neural network, you have input-output layer, you have a set of hidden layers, you have a feed-forward process and a back propagation to train the weights, right? But then you have these weights, you can train them with gradient descent, but we discussed this already. The aim of this back propagation learning is to get optimal weights that give you the best possible prediction of the network, and best possible in terms of whatever loss function you implement. Right, and so that's the key idea, but you see it here already. These loss functions, these loss landscapes for deep networks are not convex, which means we can expect lots of minima, lots of local minima. We might have global minima, but the chance of actually finding and assuring that something gets a global minimum is very slim, since we're talking about non-convex problems in very high dimensions. So we're not guaranteed to reach a global optimum, but only a local optimum. And nevertheless, the question is, how do we initialize appropriately? And this initialization is always a big issue and a big nuisance for anything that involves non-convex loss functions. This is a notorious issue anywhere in science. You know, a lot of problems like neural networks are solved by optimization, by minimizing some cost. You know, depending on what discipline you work in, it's going to be called a loss or a cost or an energy. There's different terms, but they all denote the same kind of idea, that you have some criterion that you want to optimize. And you want to find the parameters, or in the neural network case, the weights that give you the optimum. And as soon as you have a problem that is not convex, which is pretty much always, because the more realism you have in a problem, the more likely the problem that you're minimizing is not convex. This is unfortunately the case. You know, some problems can be phrased as convex problems, maybe even quadratic problems, but that's kind of a very rare minority of problems. The majority of interesting problems end up in something non-convex. And then initialization matters. And you can see it in this plot, even in one dimension. If I initialize on the left and do a gradient descent, I'll get to this minimum that you see here. If I want the global minimum, I have to initialize differently. And so the choice of initialization has a huge impact on the performance of your method. It determines to some extent where your gradient descent or your stochastic gradient descent, where it's going to end up. If you initialize differently, you will get, in general, a different result. So the question is, how do we initialize? How do we start? How do we set these weights Wi and the biases B to start off with before we do back propagation? So, and one of the issues that you can see is, you can look at, and this is very important when it comes to neural networks, deep neural networks have a lot of layers. And one, you know, we talked about the issue of the history of neural networks, that they were first introduced as shallow networks with maybe one hidden layer, right? And people didn't actually expand them to deeper networks for years and decades. And, you know, they tried, but that didn't often work well. So the theory was there that you can have a lot of layers, right? When I learned about neural networks in the 90s, the books all said a neural network has n layers, right? That sounds good in theory, but in practice it only had 3 layers, one input, one output, one hidden layer, right? And there are many reasons for that, but one is that people didn't spend enough time to understand what happens for training a network if you have more layers. And there is an issue that you face, and this is a well-known classical problem. It's called the vanishing gradient issue. And there's many variants of this aspect, but the key issue is that you initialize somewhere, you propagate through the network, and then possibly the activations from layer to layer will either decay or they will grow, and you want to have something that preserves a certain stability of the activation or the size of activation. You want to try to assure that it remains constant over the layers, right? And so you have to look at what happens to these gradients, and this is something we're going to look at. So the hidden units are all undergoing, are all going to compute the same function. Gradients are going to be the same. And the issue then is if you initialize weights with 0, that all neurons have the same property. There is no real symmetry breaking, and you have kind of a perfect balance. The gradients will also then be roughly 0 up to floating point precision, and then that's not very useful. And so here's, so one thing you can try is you can try to initialize the weights, let's say, with a Gaussian distribution. This is common. You want to initialize a bit randomly, so you sample them from a Gaussian distribution with 0 mean and small standard deviation, say 0.01. And then we can take a network, let's say with 10 layers and 500 neurons each layer. We can take a hyperbolic tangent as activation function, and we use this unit Gaussian input data for all the layers, right? And then what happens is this. So what we see here in the plots is the distribution of activations for each layer. And what you see is the initial layer has a Gaussian distributed activations, right? But already in layer 2, the activations are practically 0, and in layer 3 even more, and so the output of each layer goes to 0. And so that is obviously not nice, because then there's very little to when you do training and backpropagation layer. You don't want the layers to output to go to 0. And we can look at why that is, and the issue is really, let's say here's the tangent hyperbolic, what happens is you can see it in the hyperbolic tangent. If you get an input to a layer from the previous layer that is very small, close to 0, it kind of squashes things, and the output will then also be close to 0. And so you can see in these plots that over the layers, you see that things go to 0 very quickly. Right? Because you have this linear combination of weights, and if all the weights are near 0, then the activation, then the score here that gets piped through this tangent hyperbolic, this score will be near 0, and then the output of it will also be near 0, right? And this is something you do want to avoid, because you want in the backpropagation from layer to layer, you want to have a reasonable gradient that is being propagated. You don't want things to go to 0. So even if the activation function has a relevant gradient, as we see here, the gradient itself of the activation function is not 0, but the output of each layer is 0. And so you have a vanishing gradient that is not caused by the gradient of the activation being 0, but it's caused by the input to each layer and the output to the next layer being essentially 0. And so the small outputs of layer L, they serve as input for layer L plus 1, and they will cause small gradients with respect to the weights of the layer L plus 1. right? Because you have this, and by chain rule, so the derivative of the loss function with respect to the weights, L plus 1, is the derivative with respect to the activation function, and then the derivative of f with respect to this. And that this one is xi L plus 1, and the issue is then that this becomes very small. So then you can say, okay, why don't I initialize with very big random numbers? Isn't that a solution? If the small random numbers collapse to 0 across the layers, maybe I can initialize with very big random numbers. So let's do that. We take, again, the same network, 10 layers, 500 neurons, hyperbolic tangent, and we use unit Gaussian, but with big standard deviation 1, right? So you get activations that are very large, and saturated at -1,1, right? And then if you pipe that through the network, you see the activations remain very big. And what does that mean? It means for our tangent hyperbolic activation function, the inputs it gets are either very large or very negative, so very positive or negative. And as a result, we are in the regime where the activation function saturates. And that is also not good. So we do want to remain in the regime where the activation function is not saturated, where you have a relevant gradient, but you don't want the numbers to be near 0. So in this case, what happens is that we get a vanishing gradient in the learning that is caused by the activations being saturated. And so this is the two things you want to avoid in the initialization of the weights. You want to avoid, on one hand, that the output of each layer goes to 0 when you move across the layers, and you get smaller and smaller input to the next layers. But you also want to avoid that you get into the saturation of the activation functions, because then in the backprop learning, the gradient of the activation function here, that's going to be 0, right? So both of these aspects we want to avoid. So we don't want activations that are too large, because then we're in the saturation regime. But we don't want activations that are near 0, because then they map to 0 for the next layer. And so that is the question: how can we initialize appropriately so that we have a little bit of a balance across the layers of the activations, that they don't get too large, but they don't get too small either? And people spend a bit of time studying this issue, and there's one nice work that has had a lot of impact on this. It's a work by Gloro and Bengio, Joshua Bengio and Xavier Gloro, and since then this work is called Xavier initialization. So the assumption is we're going to start with 0 mean Gaussian noise, but what standard deviation? It shouldn't be too large, it shouldn't be too small. What is suitable? And in fact, what he did, and this is very elegant, he analyzed how can I assure that the variance of the score remains constant from layer to layer. And this is actually not so difficult to analyze, because you know what happens in each layer, right? You know what happens in each layer. You get the score function, that is this linear combination of the weights times your input. And you want to know, what is the variance of this score, and you want to make sure that variance is the same as the variance of the input, x. So the question is, how do I need to choose the weights W such that the variance of the score remains the same as the variance of x? That's kind of the idea. And that requires some calculations. It's not very lengthy, but it takes some time and some practice to do these calculations. This is something you can also go on Wikipedia and you find general rules. What is the variance, right? The variance is usually measures how is the spread around the mean. So you have the mean. The mean is the expectation of x is called its mean. And then the variance is how much does it spread around the mean. So that is the expectation of x minus mean, right? So this is, you know, the mean. Mean of a set of numbers, let's say, is the expectation of that x. And then the variance is called the expectation of how does it spread around the mean. So x minus, let's call the mean, let's call it mu. Mu is often called the mean, x minus mu squared. And that the expectation of this is called the variance. And then you can show that if you do some calculations, you can see that this is e of x squared minus the expectation of x squared outside, right? And so you have these kinds of rules to compute variance and expectation values. And you can also look at what is the expectation of two variables. Let's call them x and y. Oh, sorry, you don't see my mouse. Let me switch on my mouse. So here, if you have two variables that are independent, x and y, then the expectation of x times y is nothing but the expectation of x times the expectation of y. So for example, if you want to throw dice and x is the outcome of the first throw and y is the outcome of the second, you can look at what is the expected value for the first one. You know, if it's 6 numbers, it's typically 3.5 is the expected value, is in the middle, right? And if you want to know what is the expectation of the product of two dice that you throw, it's just 3.5 times 3.5, right? That's what you can expect because they're independent. And along these lines, you can then derive this expression where you take the score, this is this one, wi times xi, sum, and you want to know what's the variance of this score. So that is the input to the next activation, right? You want to make sure it has the same variance as the previous one. And so you can pull the variance inside. By definition, you know, it's linear, so you can take sum over I variance of wi xi, and then with some calculation you get to this expression. I'm not going to do the calculation, but essentially you just have to use these definitions of mean and variance and plug them in here, and then use this assumption of x and w being independent. W are the weights of the layer, and X is the input coming in there. You know, you can assume them to be independent. And since we know that, you know, we initialize the weights with 0 mean, we know the expectation value of W is 0. And also the input from the previous is Gaussian, is 0 mean Gaussian, but with a different, possibly different variance. And so these two expressions are 0, which leaves us with the variance of the score being the sum over I equals 1 through n variance of xi times variance of wi. And now we can assume that all the weights are identically distributed for the whole sum across the different weights. And so the sum is just n the same for x. So the sum is just n times the variance of w and times the variance of x. That is not really surprising in a way, right? So the score is attained by summing weight times input, right? And the variance of this will grow if the weight is larger, then it will increase the variance, and also it will grow if I have more neurons, right? If I have twice as many neurons, then, you know, I can expect the variance will be twice as large, and this is what explains the factor n here. So the result is pretty obvious that you would have that variance here. And so we know the variance of the score, and now what we want, as I mentioned it, what Xavier Glorieux and Joshua Benju said, they want the variance of the score to be on par with the variance of the incoming layer, of the previous layer, the signal that comes in. And as we just showed, the variance of the score is this one, and that should be the variance of x, which basically means what this indicates is I should choose the variance of the weights to be 1 over n. That's what comes out, right? And that also is not surprising. If I double the number of variables, the number of neurons, the number of weights that enter my sum here, then each should have half the variance, right? And that is a good indicator for how do I have to choose the weights in each layer, namely 1 over n, where n is the number of neurons in that layer. And so this is called the Xavier initialization. And so it shows you that you cannot choose a constant standard deviation for all the weights in your networks. They have to scale with the number, the standard deviation or the variance has to scale with the number of weights in each layer, as in 1 over n here. And once you do that, he showed it in the same example that we had with the Tanh activation function with our 10 layers, 500 neurons each. You initialize like so. And then with time, you see this is the activations, the distribution of activations across the 10 layers from layer 1 in the beginning to layer 9 in the end. And you see the activations, they don't shrink to 0 and they don't go to the saturation, but they stay in the same distribution. Very much like what we wanted. So that kind of fixes this issue. But as I mentioned, this is for the Tanh function. That's really nice. But as I pointed out, people started using increasingly the rectified linear for learning. Sorry, there's a question. That's also a possibility. In a way, I would say it might actually come out to something similar. If you rescale the variance of the weights or you rescale the Tanh function, that might, I think on some level it might even be equivalent, right? So, you know, shifting the slope of the Tanh is a little bit related to inserting a rescaled version of the input into the Tanh. And in a way, what you're suggesting is I would say, possibly even equivalent. Yeah, good idea. It might even be simpler, I don't know. It's an interesting idea. I don't know if people looked at that, but at a first glance, I would say it should probably be equivalent as a transformation. Whether I rescale the input to the activation Tanh or I modify the Tanh accordingly might be the same. Good point. And so this is good because the activations across the layers neither collapse to 0 nor blow up to the saturation. But as I mentioned, you know, around that time people started shifting to the ReLU. And if you do the Xavier initialization with the ReLU, this is what you get. So you get activations that have a certain spread here initially, but then, you know, across the layers, it does collapse to 0. Gradually, but you can see, you know, with more and more, and this is only 10 layers. If you had 100 layers, you would very soon be at 0. And you can wonder why that is. And it's actually not so difficult to see. The ReLU, what it does is, it is linear in the positive domain, but in the negative domain, it collapses, right? If this is our coordinate system, the ReLU looks like that, this rectified linear, and basically for the negative inputs, it's not linear, but it maps them to 0. So it basically kills half of your data in a way, right? Everything that is on the negative side will be mapped to 0, and as a result, that creates the collapse, and over time. But this is actually fairly easy to correct for, because what you can do is, you know, since half of your input, the negative half, is collapsed to 0, you have to rescale the variance not with 1 over n, but with 1 over 2n, right? Because you can say, in some sense, half of the data is collapsed to 0, and so the other half needs to be spread accordingly so that you preserve that, that distribution of activations, and so you choose 1 over n half, and this is 2 over n. And that is the initialization for the weights that was suggested by Kaiming and is now often called the Kaiming initialization. But it's very much the same idea as the Xavier initialization, just not for the 10H, but for the ReLU. Same idea. And a comparison shows that if you initialize the weights incorrectly, not, for example, according to this Kaiming initialization or ReLU or Xavier initialization, then you don't get any learning because of the vanishing gradients. And this is what's shown here. So this is a plot from Kaiming's paper where he shows the learning curve across the epochs, the error, going down with the right initialization and not going down with the wrong initialization. So, this is very much, taking this example where you see the activations collapse to 0 at layer 10, they're essentially all around 0. And if you have more layers, like 100 layers, this will become even more dramatic. And he shows that if you instead use this variance, the Kaiming variance, then you get a nice learning curve. The network actually learns something. So again, you see the message here as well, a message that I keep reiterating. Once you train neural networks, do make sure to plot your learning curves so that you can see whether things are decaying properly. And if not, there may be something wrong with the learning rate, or there may be something wrong with the weight initialization, as you see here. So this matters. In summary, we talked about losses, we talked about activation functions, the 10H, the ReLU, and the various variations of the ReLU, the leaky ReLU, the parametric ReLU, and all of these. And we talked about initializations, and as we just saw in the last example, initialization matters to make sure that you don't run into vanishing gradients. And so this vanishing gradient is the notorious issue that you try to avoid by choosing the right learning rate, an adaptive learning rate, by choosing something like RMS prop or momentum, etc., and also by choosing a suitable initialization. And as we saw, the key idea of these choices of initialization that people have been advocating is to assure that you maintain a constant activation size across the layers of the network. You don't want your signal to somehow collapse to 0 once it propagates through the network. And you don't want things to blow up either, because then you're beyond then you're in the saturation regime. That's the summary of this chapter, and we saw that there is different activation, different output layers that you choose for example, for binary classification, you would choose a sigmoidal. For multiclass, we saw that you would choose a softmax activation, and we saw that if you take the negative logarithm of the softmax function, you get what's called the cross entropy, or in the binary case, the binary cross entropy. The next lecture is more about training neural networks, about regularization, dropout, data augmentation, batch normalization, etc. And then there'll be more on convolutional neural networks. And that brings me to the next lecture, which is called Data Augmentation and Advanced Regularization. Why? Because we already talked a bit about regularization and we want to talk more about it. Yes? The question is whether it's mandatory to keep the activations of the same size. It's advisable. It's advisable in the sense that, as you saw earlier, if you don't initialize appropriately, then you might not see a decay in the learning. Because then what happens is that the gradients start to vanish. And if the gradients vanish, it means the update of the weights gets near zero. So in each iteration and in each epoch, nothing much happens, right? And this is the critical thing. We don't have time, you know. We have lots of weights, they need to be learned, and the backprop learning is costly if you're training for thousands and millions of weights. And so this is always, I think, a lot of these strategies are really developed and designed for large networks with many weights and many layers. And so some of these strategies may be not so important if you only have 4 or 5 layers, right? You see it, and even if the activations decrease over 4 layers, as long as you still have some signal on layer 4, that's good for training a 4-layer network. But if you want to train a 100-layer network, then you should really understand what happens with the activations from layer to layer. So recap, we talked about classification, regression classification. We talked about the sigmoidal function, how it squashes the score that comes in, S, and this is the sum of weights times the input plus the bias. And this score is squashed to the interval 0, 1 with the sigmoidal function. And we saw it can be interpreted as a probability for the label to be 1 given the input. And then we saw that this idea can be extended to multi-class classification, and this leads to this softmax function. The softmax, it's called softmax because it kind of approximates a maximum function, but softly. So in a way that this is a differentiable function. Max function is not differentiable, but this is differentiable. And we always want things that are differentiable, that have gradients, so that we can do backpropagation learning to train the weights. That's one of the key ideas in all neural network designs, is you want to have a loss that can be trained. And that means you need every component in your network must be differentiable, ideally. And then, you know, basically this is a very softmax version, and then you divide by the sum of these to get something that can be interpreted as a probability. Because probabilities need to fulfill a property that the sum over all of them must be 1. Right, much like if I throw a dice, I can talk about what's the probability of getting 6, getting 5, getting 4, and no matter what it is, the sum of them all must be 1, because it must be one of the numbers must come out. Right, and much in the same way, you need things to normalize to sum up to 1. So if I sum across all possible y's, all possible interpretations of an image, let's say, it must be either a cat or a dog or whatever, right? And if I sum all of these probabilities up, then I better get 1. Otherwise, the image is of a class that is not considered in the data set, and that's not conceivable. So this is the idea of this exponentiation. You want something that is non-negative. You want something that sums up to 1. And that's why you normalize. And then once we apply the logarithm, we get this cross entropy as a loss. That's nice. And then, you know, we talked about these activations and the fact that they often saturate, and that the gradient in the saturated area gets 0. And then we said this is why people use the rectified linear, because here the gradient is always positive, it's always constant. In fact, it never goes to 0. But in the negative regime, the regime where it's often called the dead ReLU, if the input to the activation is negative, then the output is 0. Then you have no gradients, and then it doesn't learn. That's why often people revert to leaky ReLUs. But typically we see that ReLUs are good because they offer fast convergence, and at least for non-negative input they do not saturate. Then we talked about the different initializations, the Xavier and the Kaiming initialization for Tanh and for ReLU. And these assure that the activation remains constant, or the size of the not constant, but the size of the activation, the spread remains constant across layers, the variance of it, if you will. Now we're going to talk about data augmentation. This is a very important aspect for training neural networks. The aspect is very simple. We saw it that you don't want to overfit, and still you want to, learn something reasonable. You want this to generalize well to unseen data, and you want to avoid overfitting. And one solution to avoid overfitting, this was the trade-off, we talked about it, that if you have a larger capacity of your network, more weights, more layers, more everything, then the danger is that it will start overfitting. The more parameters you have to train, the more you can tune to your training data. And so to compensate, and at the same time, you want a big network with a big capacity so that it can distinguish very powerfully complex signals, right? Cats, dogs, whatever you have in images, right? And so if you have a big network with a big capacity, one way to avoid overfitting, two ways is, one is throwing more training data at it, and another way is regularizing. And so this is what we'll talk about. And here, this is a strategy to create more training data, is a technique called data augmentation. And this is important. It's also important to understand how do we process data in order to enforce certain distributions that are easier to learn. And this is important to understand. For example, if you get data and you rescale all your data, you multiply it with a constant factor, what's going to happen? Then in principle, all the gradients will get rescaled because the signals are larger. And then you need to actually adjust the learning rate. So if you put in training data into your network that is at a completely different scale from other data, then everything gets rescaled, and then you would have to adjust the learning rate accordingly. You would have to, if you double the size of the training data, not the amount of training, but the scale of it, the intensity of your input image to a neural network, if I multiply it by a factor of 2, you can see that this training data will lead to gradients that are larger by a factor of 2, and then you will have to reduce the learning rate by 50% to compensate, and that makes the training a little bit tricky. And so what is often done is that you normalize training data. And this, there's many definitions of what you mean by normalizing, but here what people mean, and this is a very classical idea in statistics, sometimes it's called normalizing, sometimes it's called whitening. So here the idea is you start with original data, you first normalize it so that the mean, you see this is not centered around 0, this is offset, so you normalize it so that it's centered around 0, and then you normalize it in scale so that you have like a unit variance, if you will. And by scaling your data, you can change the ratio between data and regularizer weight. And since you don't want to adapt that every time, you just normalize the input data to your network. And so the normalization, it avoids outliers in various dimensions, and this is, as I mentioned, called whitening. And why is that important? Because we want to learn things with a neural network, but we typically want to have certain invariances. For example, if I train a network to detect cats in images, then I would want a network that will detect a cat no matter where in the image it is, right? And so the question is, do I need to train it and have the same cat image every time in different locations of the image? And yeah, this can be done, and hopefully the network will learn. But one elegant way is to somehow normalize the input data, or assure this invariance. And invariance is something very important in recognition and in any kind of science. You want, machine learning algorithms to exhibit an invariance to certain transformations. Translation is one of them. I want to recognize a cat no matter where I place it. But also rotation. I want to recognize a cat even if I rotate it differently. And this leads to, a lot of research that was done in neural networks on so-called equivariant deep networks that have this property that if you rotate the input, then the output of the network is also rotated in the same way. And maybe scaling as well, that I recognize a cat even in a rescaled version, right? That said, I think, human recognition isn't perfectly invariant. If I were to show people images of cars, in the case that a car is upside down and hanging in the sky, people will take a much longer time to recognize it as a car. You can imagine, and that is why, because we don't ever see cars upside down hanging in the sky, right? So, we have a certain prior of where we expect objects to be in the world, and if they're not there, our recognition systems are less likely to pick them up. And so, even though people say, yeah, we want all this invariance, I'm not sure the human brain has all of the invariances. We have a certain robustness, in the sense that if the object is rotated a little bit, we still recognize it, but once it's completely upside down in a completely unexpected location, then we will typically not recognize it as easily. Indicates that the human visual system is not fully invariant. And so what you can do for AlexNet, for example, and this was done for ImageNet classification in AlexNet, is that you subtract the mean image and then you do a normalization per channel. For example, this was done in VGGNet. These normalizations can help. And so, as I mentioned, classifiers should be invariant to a wide variety of images. For example, here you see cats in very different locations, different size, different rotation, different pose. And in a way, this always deals, if you have enough training data, then all is fine. But the question is, what if you don't? And you never ever have enough training data. And then one thing you can do is you can generate artificial training data by what is called data augmentation. And I mentioned invariance. What invariances do we want? I mentioned already translation, rotation, scale. These are pose invariances, right? And maybe even 3D pose. I want to recognize a cat even if I rotate it not just in the image plane, but even in 3D, right? Articulation, appearance as well, right? We have different cats. Some are clip art, some are drawing, some are, completely different colors, different appearance. But also illumination. So we may want to recognize a cat independent of how the lighting affects it. This is something that magically the human brain is very good at. I think by evolution, the lighting, the sun rises, it sets, the lighting changes all day long. If you had to always, redo everything in different lighting, that would be a disaster. To the extent that if I show people multiple images of the same object and the lighting changes, they don't even notice, right? We have a way of completely factoring out illumination. I see that when my kids read, they often read in the darkness, right? Until I come in and switch on the light. They didn't even notice that it's pitch dark in the room, right? This is how well the human system copes with lighting variations. It completely ignores them. And so what you can do is to bring in that kind of invariance into the network. You can do data augmentation. So you observe that the classifier should be invariant to a wide range of transformations. And what you can do is you can take your original training data and simulate tons of transformations of it and feed those in as additional training data. And this is a popular trick called data augmentation. And in my experience, that trick can be very much adjusted to the problem you want to solve. If you know what invariance you want, you can bring that in. So like very early on, years back, we had a collaboration around 2015, I think, with an automotive company, and they wanted us to train a neural network to detect construction sites on the highway from just one image. And we did it, and we found it works super well. Just given a single image, we could tell with 99% precision whether it was a construction site or not. But one of the tricks was doing heavy data augmentation. So what we did there is we first trained a network, and very quickly the network decided whenever the stripes on the street were yellow, it would say construction site, right? Because in construction sites, the strips are yellow. So this is the issue with deep networks. They are very clever. They figure out quickly what to look at, right? As soon as the strips were yellow, they said construction site. The downside was in the few cases where we had a construction site, but for whatever reason the strips were not yellow, it didn't work so well, right? So then you can feed additional training data into it, where you take all the construction site images and remove the yellow color and fade it out to white and just put those in again and say they are construction sites. But I artificially removed the yellow channel so that you don't see the yellow channel, right? And that made the learning harder for the neural network. It basically had to adjust in the training and learn that even if it's not yellow, you should still detect these images as construction sites, right? And so by augmenting the data and creating additional data where we deliberately filtered out the yellow, we made the network more powerful. And so some of these data augmentations are very problem dependent, right? This is something where, the expert can look at it and can see what does the network look at and can somehow suppress that to make sure it looks at more. It looks at the other things as well. So some things are obvious, rotating the training images in different rotations and just throwing them in again, rescaling them, right? Changing the contrast, lighting. So these are different things you can do. So let's say you start with one image, and this is an example from the famous paper of Alex Krzyzewski and collaborators that really propelled the deep networks. Without data augmentation, they have a 224 times 220. Why is it 224 times 224? I don't know exactly. It's what they chose, and a lot of people used a similar size of training images for the network. Maybe due to the GPU they had at the time, could be. So if you just have one image and you don't do any data augmentation, it's a single training sample, right? But just by flipping it, saying, it's still a cat no matter whether it's flipped, right? You can double the number of training images in one step. So that's nice, with one single step you get twice as many training samples. And then you can do a different cropping, so you can take the same image and crop different parts of it and say, even if I crop it here, 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 or here, it's still a cat, right? And then all the flips, so you get easily 10 out of one sample, you can generate 10 different training samples. And then you can go into, data augmentation where you modify the brightnesses. You take the input image and you apply various brightness transformations, contrast changes, right? That, for a human, as I said, we still see the cat and we are completely ignorant almost to these variations. But by default, the machine is not ignorant to these. It sees the different brightnesses, and if you want the system to be invariant to it, you can create all these perturbations and augment your training data in this fashion. And this is one elegant way to create tons and tons of training data. Why is it elegant? Why? Because you don't have to relabel the image. You don't have to go into nature and take more pictures, right? You just take one picture and it generates lots of training samples. And you don't have to ask the expert, is it still a cat? No, you started with a cat, so you can keep the ground truth label. Because in some applications, getting ground truth is also challenging. One challenge is going out taking all these pictures. The other challenge is asking an expert, what do I see on these pictures, right, to get the label. Here, you have one labeled image and you can create tons of labeled images for free, essentially. And so you would augment your training data by creating random crops, resizing the image, randomly sampling crops, etc. And this is what Krzyzewski and collaborators did in their paper. There is, I should say, also an alternative that you can do, and this is, I think it's called test time augmentation. So you can basically, if you have a test image that you're supposed to classify, you can create all sorts of augmentations of the test image and throw these into the classifier and see if there is one of them that it classifies correctly, something like that. This is also doable. That this is we're not going to cover this here in class because very often you don't want to have things that increase compute at test time. Because the way most neural networks are deployed is you have one computationally tedious process of training the network, but once you've trained it and you want to apply it, then things should run fast. And so you don't want to, in test time, start to augment the test image because that is just extra compute. That's why typically people focus more on the training phase when they do augmentations. There's a lot of work on data augmentation. These are two papers that I cite here that give good insights into how this works. They consider various transformations, for example, translation, scaling, rotation, flipping, mirroring, you name it, and different brightness variations that they want to be invariant to or maybe robust to. And then depending on what kind of robustness or invariance you want, you will augment the data accordingly. Let's say if you want to have invariance to rotations, a full 360 rotation, then you would maybe do 1 degree rotations in 360 times. But if you want just robustness and there are certain variations, you would have, less augmentation or more specific ones. Yes. Is the test set made larger? Typically the training set is enlarged. Yeah. I think that you can choose how you want to do it. And it's a good question. There's possibly more computationally efficient ways of doing it, yeah. But in principle, you can do both, right? I think it depends, this is a trade-off, how much time does it take to compute the different augmentations and how much memory do you have to store the training data. And if you have enough memory, then you should probably pre-compute the augmentations and store them all, because then you can access the samples multiple times at training, at test, at validation, in the cross-validation strategy, right? It might be better, then you don't need to redo the augmentations. But if you're memory constrained, then maybe it's cheap, and the augmentations are cheap to compute, then you can also do it on the fly. What's important though is in practice you really want to make sure that whatever augmentation strategy you choose, that all the original training data get augmented in the same number of times. Right? You don't want to take cat A and do 100 rotations of it and cat B you don't, right? Because then it's going to recognize cat A in rotated versions, but cat B possibly not, right? So you want to make sure that augmentation is done consistently for all training samples. What's important is when you deal with augmentation, you shouldn't fool yourself, right? So if you say I augmented the training data and indeed my network works better than some other network, then it's a little bit cheating, right? Because if the other network didn't have the augmented data to train with, then it's no surprise that your network works better. So if you're comparing two different networks or two different learning strategies, make sure you're talking about the same training data. So otherwise you're comparing apples and oranges, right? That's pretty clear. So with augmented training data, I have a different learning problem that I'm facing. It's not the same learning problem. You know, the original learning problem says these are the cats, train a network. Your augmentation creates a completely different training set, where you say these additional synthesized images are also cats, and that changes the problem that you're solving. And so in a way, data augmentation can be seen as part of your network design. And what's important is, as always, when you develop neural networks and you test them, train them, apply them, make sure to debug one axis at a time. So you first find, let's say, a suitable network architecture, and then you think about how to augment the training data. And typically when you debug neural networks, you would start with a particular hypothesis. You look at your learning curves, you see whether they decay properly. If they decay too fast or too slow, it tells you that maybe the learning rate is not right. And then you have to modify the learning rate, see if that improves the convergence, the learning curves. And then you can see if you have a feeling you're running into overfitting, then you can either try data augmentation to create more training data that would avoid overfitting, or you can revert to what is called regularization. And this is in fact what we want to talk about a little bit more now, advanced regularization. So we already talked a little bit about L2 and L1 regularization. So let's look a little bit deeper into these aspects. So if you do L2 regularization, it basically means that you add a term to your loss function plus lambda times your weights squared or something like that, right? Or let's say if I have weights theta k, I would have a sum over k, and I would sum up theta k squared and say I prefer the, and we talked about what the benefit of this is. The benefit of this is that if you have a certain amount of weight that you want to distribute across neurons, let's call it theta, and then L2 regularization favors the weight to be distributed evenly across the neurons. Why? Because theta over 2 squared plus theta over 2 squared is smaller than theta squared here, right? So if I take the L2, the sum of L2 here, this gets larger weight than these here. A larger loss than these, and since I will have an interest in having the loss small, I favor an even distribution of weights. That is the typical property of L2, and we mentioned that this is often advisable because the L2 regularization assures that every neuron contributes. You don't want neurons to go to zero because then they're not contributing to the decision process, right? So in general, this is a useful regularization to make sure that all the neurons I put into a layer actually have an effect onto the decision. And and once you do gradient descent on this, then you get this term, right? Then you have, the gradient descent, the classical, we talked about it. The gradient descent update is take the old set of weights minus epsilon, the learning rate, times the gradient with respect to your unknowns. And once you have an L2 regularizer on the weights, you get minus lambda times theta. This is slightly different from what is called weight decay regularization. Weight decay regularization looks like this. So you also have an update where you say start with the old weight and then subtract alpha times the negative gradient, with alpha being the learning rate of the optimizer. But in weight decay regularization, you basically say rather than starting with theta k, I start with something slightly smaller than theta k. Let's say 1 minus lambda, and lambda could be 90% or something, so 0.9 times theta k. So I would always start with something slightly smaller and then do a gradient descent. That has also the property of reducing the size of the weights. And in fact, at a first glance, this so-called weight decay regularization that was proposed here, decoupled weight decay regularization, at a first glance it's equivalent to gradient to L2, right? Because why? Because I have here theta minus lambda. If you take theta k minus, this is 1 times theta k minus lambda is 1 minus lambda times theta k. It looks like it's the same here, right? And in fact it is equivalent to L2 for the standard gradient descent. But it turns out it's not equivalent if you use an atom optimizer and stochastic gradient descent with momentum, etc. Then things look slightly different, because then you're actually aggregating this exponentially. You have an exponentially decaying aggregation of this weight decay. And so there is a slight difference, and both of these strategies can be useful for regularizing things. And this strategy of weight decay regularization was advocated in this 2019 paper. There is another, and so you see there's a lot of, more sophisticated regularization techniques that people have proposed. This is, let's say, a variation on L2 is this weight decay regularization. Another strategy that's often called a regularization as well, or it's called, in the literature, it's often called early stopping, is the following idea. We said that ideally your training loss keeps on going down in this typically exponential fashion. And the validation loss also goes down, but at some point we said it goes up again. And we said it typically goes up again once you're overfitting, right, in the overfitting regime. So something that people have done is that they do early stopping. So they look at the validation curve, and once the validation curve goes up again, they stop. Right? So they say, I train my network, but once it starts to overfit, I stop it, right? Hopefully then by then it hasn't overfit to the training data yet. That seems to make sense. Right? Intuitively, you would say, yeah, makes sense. You get into the overfitting regime, so don't continue going this way. But I'm not a big fan of it, I should say. I don't like this idea because it's not, from a mathematical point of view, not terribly principled, right? You start out with a loss function that has data term and regularizer. You say, this is the loss that I want to optimize, so I do some gradient descent to determine the optimal solution. But then before you actually reach that solution, you say, oh no, now I stop. I don't want to go further. Then, then everyone would say, well, then do you want to minimize that loss, or do you not want to minimize the loss? And you can't really say, well, initially I want to, but then maybe at some point, maybe I don't want to, So I don't like this. It's very fishy if I look. The other thing is very fragile, this strategy, right? For example, if the curves look like this, yeah, the validation error goes back up. So this is an indication that something is fishy. But Also, the gap between training loss and validation loss is quite massive, right? So something is not right here. The training error is way too low in a way, right? And so either you need to have more training data or you need to have a better regularization on your weights or something, right? And so this is usually the more principled solution to the problem. But the issue is, it's always easy to say just throw more training data at it. There are cases where you don't have more training data. And then this heuristic of early stopping might work, It's not beautiful, it's not very principled, but if it solves the problem, to some extent, that's what determines success in the application world, right? There is another regularization technique that is quite sophisticated and fairly beautiful, and this is techniques that are called bagging or ensemble methods. The idea is as follows: you tackle a problem and you train not one network but multiple networks. And then you run them and average their results. The question is, what do you mean by averaging their results? For example, you want to train a classifier that classifies if you have a cat or if you have a tumor in a medical image, right? So you train a lot of classifiers and they all say yes cat, no cat, right? And then you do a max pool, an average or a maximum over it, or you see if there is sufficient consensus across the different models that this is a cat. You take some majority vote, maybe 7 models say cat and 2 models say dog and 1 model says zebra. If the majority of the models say cat, then you go with cat. This would be one way to do it. And you can train these different models with different network architectures, with different number of neurons, number of layers, different loss functions, different even algorithms. You can train one with momentum and the other one with stochastic gradient descent, no momentum, one with atom, you name it, right? And then check how they work, and somehow it's a little bit, like what humans do, right? What politicians always do, right? They have advisors, consultants, and they typically have multiple consultants that they will go to and ask each of them their opinion, and then they might have more trust in one or the other. If you have one model that consistently does a good job, you would rely more on that one than on the others. You can give that a bit more weight. So very much like what a human does when he or she consults multiple experts. Like if you have a weird disease and you don't know what it is, I know people who've gone to 3, 4, 5 doctors and then not sure if they take a majority vote in the end or something. But in a way, this is a very, obvious strategy to do this. And what's good is if the errors of these models are uncorrelated, then you can expect that this averaging will improve the results. And so the overall error of this combined ensemble will be lower. That's nice. That's why you want to consult multiple people, assuming that they're independent or uncorrelated. Unfortunately, this is in the modern world often not the case. If you want to know, is climate change there, yes or no, you can ask 10 different experts. Likely they're not independent because they all read the same literature and they all have roughly the same information access. And so, then combining their answer, typically in this question you would get the same answer if you ask all experts, but there are some where the experts disagree, and so with experts it's not as easy because they're not independent. But if they were independent, then it would give you a much better insight asking multiple. And so typically, if you consult multiple experts, you would try to consult experts that are somehow as independent as possible. So here, if you train different networks, I think you can assume that, you know, they are to some extent uncorrelated. I think in this case, this is a fairly valid assumption. But it's a good question if in the design of the training of these various networks, if we can assure an independency. You know, and this is complicated, but you might also consider completely different architectures. A convnet and a resnet and I don't know, a transformer or something, and so this can be done. I wouldn't advise going to, you know, bagging and ensemble methods in the beginning, because it creates a massive overhead, right? You know, if it takes time to train one network, then training 10 networks and all the parameter, hyperparameter tuning and learning rate adaptation and all of that, that can take a long time. And that will take 10 times more time, right? And so it's a significant overhead, and what we often observe is that if you do this bagging and ensemble, then the overall improvement on benchmarks is often only 1 or 2% better, right? So one single network will do a certain percentage, let's say 97%, and then with bagging and ensemble you will get 98%. So it's a marginal improvement and a lot of compute overhead that you get. But it can play a role if you know, once you've developed networks, once you've shown their work, and once you really want to publish a paper and make sure you get the best possible score on some benchmark, then this might be a trick to get a little bit of boost. But it's a massive effort and a marginal gain. And one of the issues is, you know, for example, in bagging, you can use k different data sets and train k different networks with them, and then do, you know, some form of pooling or averaging of the output. But the question obviously is, if you have k different data sets, why don't you put them all into one big data set and train one model with it that looks at all the data and not just, it's like giving n experts only subsets of the training data and then averaging their result. You know, sometimes you need to see all variations of a cat to really understand what a cat looks like. And if you have one that is only trained with Siamese cats and one is only trained with other cats, you know, that might work, but it will typically, the question that is obvious is, why not train one big model with everything? I think it's related to cross-validation. Cross-validation is a little bit different. You also split the training data, but you still use all of it for training one network. Here you split it and you train k different networks. That's the difference. And in fact, the question is, if once you splitting the data set into subsets is fine, but you should ideally use all of them to train a given network and not each for a different network. And there is a strategy that is related to these ensemble methods, but very elegant and very powerful. And this is a technique extremely popular. It's called Dropout. I'm sure some of you have heard of it. It's a very elegant way to essentially do what ensemble methods do, but not with k different networks, but in one single network. The idea is that you take a network like you have it here on the left side. This is your standard neural network. Where is my pointer? It's gone. So this is your network that you consider, and you see there's a lot of weights between all the neurons. And then you randomly disable a set of neurons, a certain percentage. Let's say 50%, that's what's typically done. 50% of neurons I just kill. These are the ones marked with crosses, right? So there's no input going into them, no output coming out of them, which means that neuron here, for example, all of a sudden it only takes input from these two neurons, right? And so this is the same network as the initial one after applying dropout. Randomly sampled a certain subset of neurons that I killed. And what I get after dropout is a network that is a lot smaller than the original one. And so once I do that, I train that network, and that makes it harder actually. Often people think it makes it easier, but obviously to reproduce a certain classification result with half as many neurons is more difficult. The network has a smaller capacity by construction. And that makes it more difficult, but the key idea, and this is the beautiful idea of this dropout strategy, is to disable these neurons not on a permanent level, but only for a given set of update steps. So I train the neural network in backprop learning, and all the time I randomly kill a certain subset of neurons that are no longer allowed to contribute. Right? It's a little bit like if you have a set of humans that are supposed to understand a scene, and maybe you have one who is just so clever and always understands everything. If that happens, then the others never get to contribute. Maybe they sit back and say, well, he explains it all, or she, then so I don't have to figure out what the signal is, right? If there's one neuron that says, yeah, that's a cat for sure, that's a dog for sure. The other neurons, they'll just put up their legs and say whatever, right? Yeah. But if that one neuron randomly gets killed and all of a sudden the others have to work, then they start looking at the signal and start, thinking about what makes this a cat and that a dog. So they are forced to act and to kind of step in, right? And this is what you can mimic. This is very much like what you would have with a set of humans. And I've seen that a lot. If you have student groups, it happens. If you form, I'm sure you've seen that. You form a group with your peers to solve the exercise sessions. If there's one very smart one in the group, yeah, you know what I'm talking about, right? Then the others will say, well, she knows, so let her figure out. And I'll just wait what her answer is and say, oh yeah, that makes sense. I'll write that down, right? And then you don't learn much, right? But if every now and then one of them is randomly forced to shut up and say, I know the answer, but I'll not say it, you got to figure it out, then it forces everyone to learn, right? So you should think about using dropout in your peer groups every now and then. And the whole point is that you randomly switch it off, and so then you do update steps, and so the other neurons are forced to learn, right? And in some sense, what that mimics is much like an ensemble of smaller networks within one big one, right? Because once I switch off this percentage, 50% of the neurons, I get a smaller network. And that smaller network is forced to work, right? And that creates an enormous robustness. And this is very important. This is actually something that works super well in human brains, by the way, much better than in most machine intelligence. The human brain is very robust. You all know this, right? You go to a party, you drink 4 or 5 beers, and the next morning you can still perform, right? You wouldn't want to know how many neurons just died the night before. Still, the network works, right? This is what I call robustness, right? And it's different from dropout. In dropout, they are temporarily disabled. Alcohol is like permanently disabled, right? But the human brain is very robust. And it has to be. In biology, things need to be robust. Why? Because biological neurons already, they're not reliable. They're, from a technical point of view, a disaster, right? They're supposedly send out a spike whenever the input is this and that. I learned it, yeah. You take a real neuron, sometimes it sends out the spike, sometimes it doesn't. You can't trust it, right? And so if you have to have a brain that operates on individual components, none of which is in any way reliable from a technical perspective, the only way to go is with robustness. And this dropout creates a significant robustness for obvious reasons. And so if you use half the network, you have half the capacity. If you want to see an intuition for this, you know, the network is kind of forced to make predictions with fewer features. And every feature is kind of pushed to contribute because it cannot rely on another feature to be there. So the weights stay the same for these. They're not updated. And they're not used. So if you use this computation graph, you basically kill the respective edges, right, temporarily. And at later stage, you switch them back on, and you kill other edges, and yeah. So it's a fairly, and so the way you can see it is if you train a classifier to look at an image like this one and say, what is it? Say it's a dog, and then you have one neuron that checks, is it furry? Because dogs are furry, and another one checks, does it have two eyes? Does it have a tail? Does it have paws? Does it have two ears? Right? And obviously, in a way, these are a little bit redundant, right? But what you want is you want to make sure that the network still works if part of them are disabled. So if it doesn't see whether it's furry, but only sees the two eyes, and if it doesn't see whether it has a tail, but only sees that there are paws, right? Then you want the classifications to still work. And the human brain is extremely robust to things, right? We learn to use all our senses, and sometimes it's amazing how we can use one sense. You know, I can sometimes hear certain vehicles without needing to look because my ears tell me that there is a bus coming or a car or a truck. And so humans are very, very, very redundant in a way, in their way of recognizing things in the world. And so this is what you enforce with a dropout. You enforce redundant representations. You say, if I kill half the neurons, if I kill half the features, does it still work? But it's important, you know, this dropout doesn't make the learning easier, it makes it harder, and it forces the remaining neurons to actually produce meaningful results. And you can consider dropout as a model ensemble because, you know, you take subsets of the neurons and they form a smaller model, and that model should work. But what's nice is in the end they all contribute to one big model. Yes? Typically you would randomly select the weights that you kill. Yeah. And then you can think about how many in each layer, right? Should it be the 50% of each layer, etc.? Yeah, so there's different ways to do that, but typically you would do that randomly. And so in a way you can think of it as two models within one, right? I can consider this model that maybe classifies these dogs, and I consider a model 2 with the crosses here that classifies other dog images, and if I put them together in one model, then it should be able to classify all of these images as dogs. So in a way it is a little bit like having two models in one. If you consider one specific dropout. And at test time you can also do a dropout. But one of the issues once you do that is, we talked about this in the weight initialization, what is the variance across the layers, right? And we saw that with the weight initialization, we choose these initializations to make sure that the activation, the variance of the activation is constant from layer to layer. Now, if we kill half of the neurons, then the result is that the activation for the next layer and the variance of it is much higher. If we train with them off, and then at test time, so we trained with Dropout, but when we trained with Dropout, and then we apply the network at test time, switching all of the neurons on again, then if we had half of them off before, and now we switch all of them on, then the activation and the variance is much higher. Right, so you have to normalize appropriately at test time, because if at training time you only used half and at test time you use more neurons, then the score for each layer will be higher, and then the activations will be larger. And so what you need to do in PyTorch is you need to switch between these two modes, the train model and the evaluation model. So in the train model, using Dropout, you use only a fraction of the neurons. In the evaluation model, you use all of them, and so it has to renormalize accordingly. But that's not difficult, right? If you have twice as many neurons active, then you have to normalize by a factor of 2. And this is important to properly toggle between model train and model eval. If you forget to do that and you use Dropout, then things are not going to work. It's a common mistake in coding that people forget to toggle between eval and train mode. And it's kind of to assure that the conditions at train and at test time are consistent. At train time, you only had half of the neurons active. At test time, you will have all of them active. So you want to make sure that you normalize appropriately. Right? Because as I said, you have these two, let's say if you have two networks within one, right, and you trained one, then it will have a certain score function for dog, and the other one will also have a certain score function for dog, but you want to avoid, if you switch both of them on, that the score functions sum up and then you have double the score, right? That would create a bias, and so if you double the number of neurons, then you have to divide the score by 2 to normalize. It's not difficult, and this is done in PyTorch, but you have to switch so the system knows what you need to do, what you want to do. Yeah, so this is shown here. I think there's a, this is it. That if you have just one on at train time and then both on, then the expectation value of the output changes accordingly. So this is with a dropout probability of 50%. It means once you switch everything on, you have to divide by 2. So you have to basically multiply the output score with the dropout probability in practice. But what's important is we talked about dropout and how you can use Dropout to mimic multiple ensembles in a single network. So that's a very elegant way. It's something that you should definitely try out and see how it works. So what happens is that once you apply Dropout with a certain probability, you reduce the effective capacity of a model. Right? The capacity is the number of neurons that it has, right? And the number of parameters it has. If you kill half of them, then the capacity is reduced by 50%. That makes it more difficult for the network to learn. And so it does increase the training time. It makes it harder and longer to train. But it often improves the performance significantly. And it's something, it makes it much more robust for obvious reasons. It's a very efficient regularization technique. And so in practice, when you train a network, what you would do is you would look at the learning curves, as I mentioned, and if you see and observe some form of overfitting, then you can deploy L2 regularization, and you can employ dropout that can be combined, and you can do data augmentation to create more training data and see how each of these steps affects the learning and improves it, hopefully. Now that was before. There's some issues in the next sections. We'll talk about batch normalization. This is a technique where we look at the distributions of activation and the issue is that this dropout doesn't work well with batch normalization. And so it's gotten a little bit less popular now because people nowadays often do this technique called batch normalization that we'll talk about next. But if it doesn't work well with dropout. The other issue is that the training takes longer. So typically it takes like 1.5 times more training time if you use dropout. What's nice though is that this dropout, since it kind of mimics an ensemble of networks, it allows you to infer a notion of uncertainty. And this is a very important and has been a big challenge in deep learning for many years. Deep networks were from the start, when they got popular, really powerful to do classification, things like that, right? But they never came with any notion of uncertainty. They said cat, dog, house, airplane, and you never knew how certain is my model that this is really a cat. And this uncertainty in practice is super important. Let's say you're a doctor, right? And the system tells you, yeah, the patient has a tumor, yeah, the patient has cancer. You would want to know how certain is this model, right? And the patient will want to know for sure. And it's possible that the model is very uncertain, right? But a model that doesn't give its uncertainty is not very useful in practice. Because the doctor doesn't know, can I rely on this decision or is it possibly wrong, right? And so increasingly over the last years, people have asked, can we not assure some form of uncertainty estimation? And if you do ensembles and bagging, then you can do that. You can ask 10 models. If they all agree that this is a cat, then it's very likely a cat. But if only 5 of 10 models say it's a cat and the other 5 say something completely different, then there is a high probability that it's actually not a cat. And so from looking at ensembles and looking at dropout, you can infer some form of uncertainty. And this is something that was propagated a lot by people like Yarin Gal and his PhD advisor Zubin Garamani. And this is what we can look at, how we can use dropout for this. And this is called Monte Carlo dropout, and this is a little bit different. So from the standard dropout, where you typically kill 50% of the neurons to get more robustness, here you can use dropout to make the softmax probabilities, the classification results, more calibrated. You know, we said you can interpret these softmax results as probabilities, but only because they're between 0 and 1 and they sum up to 1, right? And they were kind of built to sum up to 1. To what extent the softmax output can really serve as a probability, experiments showed it didn't really work well as a probability. But once you deploy this Monte Carlo dropout, you can actually start to interpret them as real probabilities for this to be a certain class. And what you do is that you use dropout with a low probability, say around 0.1 or 0.2. And at inference, you run the same image multiple times, say 25 to 100 times, and you average the results. And so you use the dropout not just in the training, but also in the inference. And then you get different results. It's like asking different models every time, right? And then you can average the results to get the overall result, but you get also something of an uncertainty. And this was developed and elaborated in a set of papers. Yarin Gal did his PhD with Zubin Garamani, is a very famous statistician and machine learner in Cambridge. In Cambridge, and I think Yarin is now in Oxford himself. And this is a very popular direction that they pushed here in these papers, a direction that comes under many names, but one of them is reliable AI. That we want AI methods that are reliable, that are trustworthy, and you can only trust the system if it can tell you some notion of uncertainty that comes with a certain classification. All right, the next part is on batch normalization, and this is what we'll cover next time. See you next week. Thank you.